Good day, my name is Cameron Matthews and I'll be talking about the following topic today: energy and charge density analysis of non-covalent interactions within conformers of bis-2 pyridylmethylamine using ab initio couple cluster and MP2 theory, a molecular tailoring approach. Non-covalent interactions play an important role in the fields of pharmaceutical development, catalysis, host case chemistry, molecular electronics, and other concepts in supramolecular chemistry. Cumulative contributions of intramolecular interactions can result in significant deformation of the geometry of organic molecules, in particular large biological molecules. The small molecule bis-2-pyridylmethylamine serves as a test system or molecule since it does not contain highly electronegative atoms and therefore yields weak interactions, and numerous conformers exist for consideration. It is also symmetrical and contains a bridging moiety consisting of sp3 hybridized atoms, which allowed for a broad range of non-covalent interactions to be examined. The molecular tailoring approach considers the decomposition of molecular potential or electronic energy into intra- or inter-fragment pair contributions at any level of theory, for example coupled cluster. Quantitative and qualitative analysis of the intramolecular component interaction energies can be performed, and their contribution to the net stability of conformers or specific conformations may be evaluated in terms of the following non-covalent interactions: hydrogen bonding, attractive or repulsive van der Waals interactions, pi stacking, London dispersion, etc. Correlation between the structure and the nature of the interaction between fragment pairs may be evaluated via both energetic and charge density-based perspectives. Local correlation quantum mechanical calculations were performed in vacuo via the ORCA 4 or 5 electronic structure package. 224 geometry optimizations were performed at the second-order Moller-Placet perturbation level of theory. 32 unconstrained optimizations were performed for all conformers. 192 constrained optimizations were performed for all molecular fragments where the physical atoms were frozen in space. 480 single-point energy calculations were performed for all conformers and molecular fragments. At the couple clusters, singles and doubles with perturbative triples correction level of theory, 128 electron density Gaussian cube files were generated via the relaxed density matrices calculated from the DLP&O MP2 level of theory. Charge density domain analysis was carried out using Python scripts interfacing with a wave function analyzer multi-WFN. Analysis was complicated by the presence of the following non-physical errors: global polarization errors and local polarization errors. The following HPC resources was used during all calculations. The SMP queue was used and the Big Mem queue was also used. The memory allocation ranged between 96 gigabytes and 800 gigabytes, where the memory was the primary bottleneck in the couple cluster calculations. Here is an example of the molecular tailoring approach for the evaluation of the dimethylamine intermethyl interaction energy or property for conformer A. There are three representations given here: one molecular representation of the MTA approach, one via core diagram, and one of the mathematical operations involved in determining the MTA-based energies. For non-physical H11 and H12 atoms shown in red here, their coordinates were determined from constrained geometry optimizations of the largest fragments containing them. Non-physical atom-based error is expected to become more significant for interfragment interactions that are separated by a low number of covalent bonds. That is, the proximity of the non-physical atoms with regards to each other plays an important role. Here is a list of the 15 molecular components used in the molecular tailoring approach for each of the 32 conformers, where the largest fragment was the methylpyridyl methylamine fragment and the smallest was ammonia. A total of 480 single-point calculations were performed for full molecular tailoring decomposition of all 32 conformers of DPA. The molecular fragments consist of methylpyridine, 2-picoylamine, ammonia, pyridine, methylpyridyl methylamine, dimethylamine, methane, methanamine, and DPA. The following equations were used to determine the interfragment energies. A. Interfragment interaction energies relative to molecular fragments. B. Relative interfragment interaction energies relative to the global minimum of the molecular fragments. The large number of calculations necessitated creating Python scripts to accomplish the following tasks: to parse output files, to create input files, visualize data, calculate interfragment energies, and to determine atom pairs of interactions and distances for core diagrams, etc. Method validation was performed for all 10 interfragment pairs. This graph shows the reference energy as a function of conformer ID, where the conformers are ordered in order of decreasing conformational stability from left to right. By combining the following relative interaction and internal energy terms to yield the sum of terms, an excellent agreement to the relative conformer energies was achieved. The graph on the left-hand side shows the stabilizing and destabilizing interfragment components with regards to their molecular fragments for all 32 conformers. Here we zoom into the interaction energy plot to show the interfragment energies and highlight selected interpyramidal non-covalent interactions. Here is the most stable interpyramidal interaction, primarily as a result of hydrogen bonding, whereas the most unstable interaction was as a result of slight steric repulsion of the pyridyl lone pairs for conformer 12. The van der Waals interaction was the weakest for conformer 10. The parallel displaced pi-stacking interaction yielded an interaction energy of minus 1.68 kcal for conformer 28. It can also be observed that the most stabilizing type of interaction is the inter-methylene interaction, followed by the amine pyridyl interaction. The full conformer ensemble is shown here, and their structural descriptors are indicated for classification of conformer geometries. Due to the nature of the weak interactions, it is difficult to qualitatively establish the relative order of the stability of the conformers by visual inspection alone. Here the L-shaped backbone is indicated by these two lines, the U-shaped backbone by these three lines, the V-shaped backbone by these two lines, and the linear shaped backbone by this line. Preliminary charge density analysis was carried out to evaluate global polarization effects with respect to the observed interpyramidal interaction. Analysis of the Gaussian cube files considered the total or global charge polarization or partial charge polarization, where the selection of the isosurfaces via minimization of global or local polarization error was paramount. Theoretically, positive or negative charge density is correlated, that is, the same number of electrons must be displaced as a result of a specific non-covalent interaction. The sum of the integrals of charge density domains should equal 0. Polarization errors occur at longer range, therefore local atom-centered polarization should be preferred. Domains can be evaluated with regards to the following targets: volume or electron occupancy. Evaluation of the integrals of total or global charge density showed poor agreement with regards to the reference energies for all 32 conformers. Local polarization is currently being evaluated. A Python script coupled with multi-WFN is being developed to identify suitable ISO values enclosing atom-centered domains. On the right-hand side, the interactions domains are shown for interpyramidal interaction within conformer 4, with the red domains indicating positive charge density and the blue domains indicating negative charge density. Note that the domains of the methylene and amine atoms were artificially removed here. In conclusion, MTA allows for decomposition of abstract total conformer energies to yield approximate interfragment interaction energies at a chosen level of theory, thereby enabling their qualitative and quantitative characterization with regards to class of interaction and strength of interaction. This enables understanding of the theoretical nature of non-covalent interactions and will also assist with the development of force field methods for the determination of accurate non-bonded energies for large chemical systems. I would like to acknowledge the following organizations for their support.